Well, hello, NATR 346. This talk is to introduce you to Module 8 of groundwater quality. As explained here, it's a relatively small module. I have groundwater quality chapter I want to introduce you to in this talk, some lecture notes I'm going to go through, and then you'll also see a, a pretty small assignment that asks you to go into California's groundwater quality database. It's going to be less cumbersome than the other assignments. I do walk you through it here. And you can go and surf around and look at groundwater quality from wells in your area. And it's kind of a cool tool, a good way to access data, and a good way to get a deeper understanding, I think, of groundwater quality. But for this talk, I want to stay with the conceptual ideas about groundwater quality and tie it back into water chemistry talk from a previous module. So first of all, this chapter is pretty short and to the point. That's why I like it. It's just kind of the bottom line about what's going on with California groundwater quality. It talks about the contaminants, the main contaminants, and their sources. And here, right off the bat on the first page, is a nice listing of the ways that contaminants can get into aquifers. Infiltration of surface water, soil, sediments, and rock. That is the number one method of how we get contaminants into groundwater. You can also get the second bullet, is very important, direct flow from surface water. And we don't have this so much in California, but you can have situations where you have fractured rock, like in the Sierra Nevada, bedrock. And if you have contamination on the surface, that can go right through the fractures. And that's important because when the groundwater infiltrates through soil and sediment, sometimes some of the contaminants can be removed. I want to talk about that a little bit. And then here's one that people don't think about too much: direct flow through improperly constructed wells that become conduits. So a groundwater well, to put in a well into the ground, you drill a big hole and you fill it in with, hopefully you build it properly so it isn't a conduit, but it's a vertical hole that goes through layers of earth. And if that well is not constructed properly, sure enough, contaminants can enter into the well and get down into the aquifer. So this paper, though, I think, like, again, it does a good job of laying out the main contaminants that we're dealing with. And there's some important distinctions to be aware of. I don't want you to memorize the attributes of chromium and arsenic and all this information, but there's some categories of things I want you to be aware of. One is anthropogenic contaminants, man-made contaminants, human-made contaminants versus naturally occurring. And this is a very, very big deal because it turns out that perhaps the majority of our groundwater quality problems in California, maybe not the majority, but a big part of them is from naturally occurring contaminants. That is chromium and arsenic. Arsenic is naturally occurring. It's an earth element. It leaches out of the rock and into groundwater and gets into the groundwater, and we get exposed to it. And it's a problem, but it is not a human-induced, it's not an anthropogenic problem. So that distinction is important. And the other one that isn't mentioned here, kind of touched on, but the difference between organic and inorganic contamination comes up. I want to talk about that, and that ties into a previous talk. It turns out that inorganic chemicals, those ones that dissolve in water so well, are more likely to enter into the groundwater system. So I have some notes here attached I want to review with you. Remember, in the water quality lecture, open sorry, do this idea that there are certain chemicals. This case is a sodium atom, from a salt molecule, sodium chloride, is positively charged, inorganic, and the water loves to dissolve this stuff. It literally almost binds to it by having the negatively charged oxygen part of the molecule stick onto it. The significance there is that when this sodium is dissolved in the water, it's very hard to remove. There's this also, this is a repeat slide, kind of a cartoon model of when you take salt, sodium chloride, put it in water, the negatively charged chlorides break apart and they get surrounded by those little plus parts of the water molecule, and the positively charged sodium takes off and gets surrounded by the negatively charged parts of the molecule. This is all refresher, and this is how a salt, an inorganic chemical salt, dissolves in water. The significance of that is that it's really hard to remove them. If you want to remove a salt from the water, you either need to literally boil it off, and this is a crude diagram of a flash distillation chamber, where you just take the salty water and boil it and have the condensate, the water vapor, catch that, and you get some clean water that way. You can imagine that takes a lot of energy and time. The other way that's more popular these days, again, is this reverse osmosis. This is mentioned in Water 4.0, mentioning it here, and it's going to be a big deal when we talk about direct potable reuse in the next module. But this is a technology that, in this essence, shoves the water through molecular sieve, where these holes are so small that they only let water molecules through and they block off other molecules. The reason I'm bringing this up here is that if you have a contaminant that's dissolved in the water and you release it to the ground, you can imagine that that contaminant is just going to go with the water down into groundwater. Having it sift through the soil is not going to help clean that water out. So if you have salty water on the ground and you flood the field, that salt will go right down with the water into the groundwater. This is as opposed to, again, organic molecules that are based on carbon, and those carbon molecules don't have that charge to them. They're neutral. So the water, in essence, isn't very interested in the organic molecules, kind of repels it. Oil and water does not mix. And so therefore, in the world of treating water, that's a good thing, because you can then take the water and percolate it through carbon. Carbon is an organic substance, and the organic molecules in the water will love to dissolve into and attach to the organic carbon. So the result is contaminated water comes through, trickles and filters through the carbon, and it comes out clean. Why is this important for groundwater? In that if you have a contaminant that's organic, it won't dissolve that much in the water, and if it does get released to the ground, and it does filter through and percolate through the vadose zone, remember that? As it percolates through the vadose zone, well, sure enough, there's organic matter in the soil, and so the soil acts just like this carbon filter. Not as intense. These carbon chambers, for example, are 90% organic matter. The soil is maybe 3 or 4% organic matter, but still, the beauty of it is if you have organic contaminants, they will tend to stick to the soil and let the water go through, and therefore purify the contaminated water naturally. That's for organic chemicals. For salt chemicals, not so much. In fact, not at all. And so here is a chart that I think is important. Again, it's not to memorize. The point here is, what are the big chemical contaminant problems in California groundwater, and what's naturally occurring and what's anthropogenic. This chart is from a study that the state of California did a few years ago, and it lists the number of water supply wells that have been impacted by these different chemicals. And so you can see the number one chemical that is causing the most problem for wells is arsenic. And arsenic, as you know, is naturally occurring, primarily. There are places where, there are cases where a certain industrial waste or something has arsenic in it. That can happen. But it, basically, the problem with arsenic is that it's found in Earth's crust naturally, and that the rock and soil material, the arsenic leaches out of it and it gets in our groundwater. So our biggest problem is naturally occurring arsenic. The next biggest one is nitrate, and that's due to primarily agricultural activity. I want to get into that a little bit later. And the thing you might notice about both of these is that they are inorganic, and that is that they dissolve in water, and therefore they're hard to remove from the water. The third most common contaminant is what's called gross alpha particle activity. That's radioactivity, literally. And that surprises folks, but granite, naturally, Sierra Nevada are made mostly of granitic rock. And that granitic rock has a lot of radioactive elements in it. And when you take that rock, and again, with the weathering we learned about, breaks apart the mountain, carries it, the rivers carry it down and pulverize it into sand and silt and deposit it in the valley, that broken up granite has radioactive elements in it, and that leaches into the water and gets down and is a contaminant of concern, and it affects a lot of supply wells. These other ones, you can see they're orange. So nitrate is orange because even though it occurs naturally in the environment, it's anthropogenic is the reason we have so much of it, and we have so much of nitrate mostly, again, because of the Haber process, which I think is kind of amazing. These are perchlorate, PCE, and TCE are the most common industrial anthropogenic chemicals that are in groundwater. Uranium is followed. So you can just take a look at this. Maybe you'll recognize some of the chemicals from the news. But again, I just want the takeaway is, which of our main chemicals are anthropogenic and which are naturally occurring, and which are inorganic and which are organic. Between this chart and the water chapter, I think that's all there. So, yeah, I showed this earlier, I believe, that just sort of the model of, putting a bunch of nitrate on the ground, irrigating crops. The nitrate is needed as a crop food, and the nitrate can be synthetic, and or it could be cow manure. And if the crop doesn't take it up, well, it's dissolved in the water. It's going to make its way through the vadosome. Again, the key here is if it's dissolved in the water, it may have a long way to go through the vadosome to get to the groundwater. But if it's dissolved there, it doesn't matter. It'll all get down there. So that's why nitrate is such a problem with our groundwater. California recently has done quite a bit of study of the nitrate problem, and it links up to a big initiative we have in California you may have heard of called the Human Right to Water. Our governor signed Human Right to Water, I think in 2008 or something like that, that said every California has a right to safe and affordable drinking. And one of the biggest issues, one of the biggest contaminants that there are that are affecting people is nitrate, especially disadvantaged people living in rural ag areas. You can imagine if you're out in an agricultural area surrounded by irrigated agriculture and you have a well, usually a shallow well, because if it's a domestic well, just taking care of your house, you don't need to drill a very deep well. That's expensive. So if you're a domestic well out in Bakersfield, Fresno area, you have a shallow well surrounded by agriculture. There's a high chance there's nitrate in the area, and nitrate at concentrations above the maximum contaminant level. It's a very big problem in California. So this report goes into that, and the details, the sources of nitrate, where it is and where it isn't. Out of that report is kind of interesting. It talks about the total amount of nitrate loading into our groundwater system. And you see cropland is 94% of the source of nitrate. People, when you're driving around and you see a dairy, an animal corral, and you see piles of manure and piles of cows and stinky stuff, you might think, oh my gosh, that's the pollution problem. And well, it is. But compared to cropland, putting manure out in the field, taking synthetic fertilizer, spreading it around, making sure that you have enough so you get a good yield, that's the biggest problem by quite a bit. If you grew up near dairies or like I did in Modesto and you know where some manure storage lagoons are, well, that you might also conclude that that would be a big problem. And again, locally it is, but it's not as big as cropland. And then finally, septic systems do cause people a problem. When you have a small property and you're not on a sewer line, your poo goes right to the septic system into the backyard. Theoretically, a lot of it will get treated by the soil microorganisms, but again, the dissolved nitrate will not, and that will go through and infect the shallow groundwater, and it's very common for that to also impact your well. So I want to move on to that's the nitrate problem in California, and you can. This is just a map to illustrate that tool that I introduce you to. This is a plot from that tool that just shows if it's a red dot, it's a well with nitrate above 10 parts per million. And this is the Salinas Valley area. That's been a very known high impact area, lots of agriculture. And then this is Tulare, Bakersfield, Fresno area, lots of nitrate, lots of wells. And again, if you live out here and you're on a well like that, it's a problem. And and a lot of people on domestic wells don't have their well sampled; they don't even know. And so there's a lot of work being done now to hopefully address that through Human Right to Water initiative. The other inorganic chemical that is also a big driver for problems in California groundwater is salt, TDS, total dissolved solids. And here is a case where, as we'll get into infrastructure, I think, in the next unit, but how we take water in California and take it from the north where it rains and move it to the south where we want to grow food, where there are people, LA and swimming pools and all that. When we take water, we use the delta to convey that water. So this is Shasta Dam. We take that water from Shasta, we open up the dam, it goes down the Sacramento River, it goes into the delta, and there it gets a little salty. It picks up salts, naturally occurring salts. The water in the delta is pretty good quality, but it has some TDS, it has some salt in it. You take that water with a little salt, bring it down to a dry area and grow food, you'll grow a lot of food. But remember the problem, well, evapotranspiration, probably the most favorite term of the class. If you have water with a little salt and you put it on a plant, the plant will take up the water and leave the salt behind. And that's what that salinity paper is about. This little cartoon, I love it. Here's this little dot here. This is a water droplet with salt in it. The little red dots are like sodium chloride. Let's say the plant is ingenious at getting the water out, leaves the salt behind. So what happens over a long period of time is we're basically just taking a bunch of salt in the water and dumping it down here, and it is accumulating. It has been responsible, this mechanism of salt accumulation has been responsible for significant changes in civilizations in history, because we've known a long time, since Water 1.0 or earlier, it's great to irrigate a dry area because it's hot and dry, long growing season. You just bring water to it and you've got great agriculture. The problem is the salt accumulation. And definitely we're seeing already, for sure, TDS in groundwater increase and crop yields decrease. and farmers are changing to different varieties of crops that are more salt tolerant, and actually just going ahead and following fields. It's not, it's a slow, creepy process, but the writing is on the wall, and there's efforts in California to address this. What are we going to do? One answer that's on the table is to pump out the salty water, pump it out of the ground, run it through reverse osmosis, and then you have nice clean water to irrigate with. The problem with, by the way, the problem with using reverse osmosis is when you take salty water and shove it through a filter like this, yeah, you get great water coming out. But what do you do with this yucky stuff on the other side? It's salty, brine-like stuff that you really don't want. So disposing of this waste is a big problem with this technology. Not only is it expensive, but what do you do with the waste? You've probably bouncing around a little bit here, but this is the technology that's used for desalination that we'll get into in the water solutions part of the class. If you take seawater, shove it through a reverse osmosis system, basically it's 2 to 1. It's 2 gallons of seawater for 1 gallon of fresh water on this side. So great. What do you do with a gallon of yucky brine waste after you've shoved it through the filter? If you live near the ocean, that's great. You can just dump it in the ocean. We don't just dump it, but you release it to the ocean. If you're down here in the Central Valley and you've treated a bunch of water with a reverse osmosis, what do you do with that brine? And that's a big problem. One solution might be to put in a 300 or 400-mile pipeline and ship it back out to sea. These are expensive and big issues. And so I'm emphasizing this so much because, with news and movies and such, you think of groundwater contamination. A lot of times you think gas stations, polluters, factories, they look bad. And certainly those cause problems for groundwater. But the big, big drivers in California, certainly in the Sacramento area, are salt and nitrate. All right, so that's kind of just some concepts I wanted to get across in this talk. The main thing about the groundwater unit here, groundwater quality unit, is just to understand the major chemicals and the concepts in that chapter in this talk. And then I hope you have a semi-enjoyable time surfing around the California groundwater tool there in that assignment. Talk to you later.